Today, we are jumping straight into a paper called BDH-CQ, In Context Learning with Recurrent Latent Reasoning by researchers from Pathway, BDH-AI, and NYU.
Yeah, and if you're an AI researcher or, an ML engineer trying to squeeze out every drop of inference efficiency, this is the paper you need to be looking at.
Exactly. I mean, we are talking about a tiny 150 million parameter reasoning model here, and it completely drops traditional text-based chain of thought.
Right. It doesn't spit out intermediate text tokens at all.
No, it just processes demonstrations into recurrent memory, thinks iteratively in this high-dimensional latent space, and then, boom, just outputs the final answer.
And the results are honestly kind of wild. On ARC-AGI 1, it hits a 29.5% pass at 2 rate.
But at an absurdly low compute cost, right?
Right.
Like 0.0007 per task.
Exactly, which completely shatters the cost efficiency Pareto frontier. I mean, it operates up to 57 times cheaper than frontier models like GPT 5.6 Luna.
Yeah, 57 times. It's crazy. Welcome to AI Paper Slop, by the way. Let's unpack how this thing actually works.
Yeah, so to understand why they built this, you really have to look at the bottleneck of serial narration.
Right.
We've become, incredibly reliant on forcing models to basically talk to themselves to solve hard problems.
Like using chain of thought as a scratch pad.
Exactly. It gives the model time to process complex logic, but the problem is it tightly couples the actual act of reasoning to the generation of language.
Which is, okay, let's unpack this. It's like forcing a math prodigy to show every single step of their algebra homework out loud, word for word, before they are allowed to write down the final answer.
Yeah, that's exactly what it is. And think about the mechanical reality of that on the GPU. Every single intermediate state, every partial hypothesis has to be projected out of its continuous hidden dimension.
Right.
Forced through a discrete vocabulary, emitted autoregressively as a token, and then consumed again by the entire network before it can even take the next step.
See, I have to push back a little here just because, as an engineer, chain of thought is what actually made these models useful for complex, verifiable logic, Like we saw this with DeepSeek R1. It works.
Oh, it definitely works.
So why are we trying to fix a paradigm that is fundamentally, driving the current state of the art?
Because the cost of that coupling is just astronomical at scale. Every token you emit means your key value cache, your KV cache, is just ballooning in size.
Oh yeah, the KV cache blow up.
Right. In a production environment serving thousands of users, that blow up is what actually kills your throughput. You literally run out of VRAM just storing the intermediate thoughts before you even get to the answer.
Which is the ceiling on current scaling.
Exactly. So the researchers contrast this with continuous or latent reasoning. They actually point to human cognition. Neurological work by Fedorenko and Varley shows that advanced conceptual reasoning in humans doesn't strictly require the language network.
Wait, really? We have distinct systems for that?
Yeah, distinct brain systems for language and logic. So by moving the model's reasoning into a continuous hidden state, it can explore multiple solution paths simultaneously without serializing every thought into an English word.
Okay, so we've eliminated the text token bottleneck. But that creates a massive black box, doesn't it?
It does.
Like if the model isn't generating words, how do we actually know it's learning from a prompt and not just, doing shallow pattern matching?
Well, that's where we have to look under the hood at the BDH-CQ architecture.
Right, because if it doesn't have a massive KV cache, how is it holding on to the prompt demonstrations at all?
So it builds on this sequence model they made previously called the Dragon Hashling, or BDH. It uses these ReLU low-rank transformations. But the core innovation here is how it cleanly separates memory from reasoning.
Okay.
So the first part is the recurrent memory, which they call S sub T.
Now, if you're an engineer listening to this, alarms are probably ringing in your head right now. The moment anyone says recurrent state, you immediately think of like old LSTMs and RNNs, right?
Oh, for sure. Vanishing gradients.
Yeah, exactly. Vanishing gradients, forgetting everything after 50 steps.
Yeah.
So how does it avoid catastrophic forgetting?
It avoids it by redefining in-context learning. Normally, with a transformer, you're building a massive physical filing cabinet for the KV cache. Every token gets a file.
Right.
BDH-CQ abandons the filing cabinet. It processes demonstrations sequentially, but instead of storing them, its recurrent state updates dynamically. So the state at step T is just a function of the state at T-1 and the new demonstration at T.
Wait, So it's more like a single whiteboard.
Yes, exactly like a whiteboard.
It reads a demonstration, updates the mathematical summary on the whiteboard, and then moves on.
Yeah.
So later inputs depend entirely on the associations it built up from the earlier ones.
Exactly. It absorbs the structural relationships without keeping an explicit cache of every single pixel it just saw.
Oh, wow.
And once it ingests all that, it moves to the second conceptual role, which is latent reasoning, or H sub R.
Okay, so this is the actual thinking phase. But again, if it's not looping through an autoregressive generation cycle, what is the computation? How does a forward pass actually think?
So it receives the query it needs to solve. It encodes that input into an initial latent state, H0. Then it iteratively transforms that hidden state going to H1, H2, H3, applying computation purely in this continuous high-dimensional space.
And then it just spits out the answer.
Yeah, once it finishes its allocated reasoning steps, it decodes only the final answer.
I want to make sure the gravity of this hits home for you listening. Memory, adaptation, and inference are woven into the exact same computational fabric here. And there is no backward pass.
Right, none.
It achieves all of this without updating a single parameter at inference time. It's pure forward pass latent iteration.
Which is elegant, but, an elegant architecture is totally useless if it hallucinates or fails at basic logic.
True. So we've established how it thinks, but let's look at the benchmarks to see what it can actually solve. They tested this using ARC, the abstraction and reasoning corpus.
And for a model trying to prove it doesn't need language, ARC is basically the perfect test bed.
Because it's all visual, right?
Exactly. It strips away any reliance on linguistic fluency or memorized trivia. You just get sparse visual demonstrations, like 2 or 3 examples of a grid of colored squares turning into another grid.
Right, based on some hidden rule.
Yeah, and you have to infer that exact visual transformation and apply it to a novel test grid. It strictly tests fast in-context generalization.
And the results on the public ARC-AGI-1 evaluation set are just wild. This tiny 150 million parameter model hit a 29.5% pass at 2 metric.
Which was independently audited by Bielek and NYU, by the way.
Yeah, so it's a robust number. But the score itself isn't even the real headline. The headline is the cost.
The cost is unprecedented. The inference compute costs 0.0000700 zeros per task.
Wow.
That's under 0.85 H200 GPU seconds.
To put that in perspective, if you look at the ARC prize leaderboard from around August 2026, BDH-CQ is about 57 times cheaper than GPT 5.6 Luna Low.
Yeah.
Luna Low scores slightly higher, like 34.2%, but it costs 4 cents a task. 4 cents versus a fraction of a tenth of a cent.
Even factoring in OpenAI's API price / like that 80% cut in late July 2026 BDH-CQ is still about 11 times cheaper.
It just creates an entirely new operating point on the cost-efficiency Pareto frontier. Because for so long, we just assumed you had to pay the massive compute tax of a token-spewing LLM to get state-of-the-art visual reasoning.
Right. It proves that assumption completely false. As long as your latent architecture is designed to iteratively process context, you can get frontier-level reasoning at a fraction of the cost.
But, an average top-line score is just an average. As technical people, we want to know exactly where this architecture breaks down. Where are the cliffs?
So the researchers ran it through ConceptARC to find that out. ConceptARC organizes tasks into 16 families to act as a diagnostic profile.
Okay.
On the positive side, it is great at concepts like extending a line to a boundary or determining if a shape is filled or not filled.
But it struggles with other stuff.
Yeah, it struggles heavily with tasks requiring copying a complex motif or ordering objects by size.
And there's a big performance gap there between test pair accuracy and strict task accuracy, right?
A massive gap. It might look at a prompt, solve the first test grid perfectly, but then completely fail to apply the exact same rule to the third grid.
So it's inconsistent.
Very. And this raises a crucial question about how these models generalize. When it fails a complex ordering task, is it failing because its absolute reasoning capacity is capped? Like, does a 150 million parameter model just lack the floating point operations to solve it?
Right. Or is it failing because it just can't extrapolate a rule beyond the complexity of the specific examples it was shown? I love this question.
That's the big one.
Because if it's a compute limit, the architecture is fundamentally bottlenecked.
Yeah.
But if it's an extrapolation limit, then it's just a prompt engineering problem, basically.
Exactly. So they designed a controlled scaling experiment. They isolated 4 skills: propagation, copying, ordering, and nesting, and pushed the complexity way beyond the demonstrations.
And what happens?
Well, for propagation tasks like extending a line until it hits a wall and copying, it extrapolates perfectly. It was only shown a distance of 3 in the prompt. But tested on a distance of 8, It solved it flawlessly on every single held-out output.
So the latent space intrinsically understood the continuity of the rule. It didn't hit a ceiling at all.
None at all. But then we hit the cliffs.
The ordering and nesting tasks.
Yeah, for ordering bars by height, performance just falls sharply when the sequence hits length 6, and at length 8, it collapses completely. Only a tiny fraction even produced a grid with the correct dimensions. It totally lost the structural plot.
Wow. And what about nesting? Like recoloring cells inside layered frames.
It holds up fine through depth 4, but fails entirely at depth 5.
But the way it fails at depth 5 is so fascinating.
It is.
Because it didn't just spit out garbage. Out of all the failures at depth 5, every single one had the exact correct grid dimensions. The pixel-level cell accuracy was over 99.9%.
Right. It usually just misses a single containment decision on the innermost layer.
Exactly. It clearly understood the structural geometry. It just dropped the ball on one specific relational step.
Which implies it has the execution capacity, but it just lost track of the rule's depth. So to test if this was an execution limit or an extrapolation boundary, they gave it supported context.
Meaning they just put one single demonstration at the target complexity into the prompt.
Exactly. Just one depth 5 example alongside the simpler ones.
And the recovery from that one example is incredible. I mean, depth 5 nesting jumped from mostly failing to flawless recovery, 24 out of 24 correct.
It just needed to see that the rule was allowed to go that deep.
And for the length 8 ordering task,
it went from 0 correct solutions to solving more than half of them just by seeing one length 8 example.
So the capability was always there. It has the latent capacity for a depth 5 relation. It just didn't infer it should generalize that far from shallow examples.
Right. It proves that for this architecture, the issue is largely an extrapolation boundary. Ordering still has some execution friction, sure, but the context support makes a massive difference.
Which means for developers, if you're designing prompts for these continuous reasoning models, the complexity coverage in your examples is just as critical as it is for autoregressive LLMs.
Yeah, you can't just rely on zero-shot extrapolation for high-depth logic.
So we've seen how it handles single operations. But real-world reasoning requires combining skills. Can a latent space cleanly compose multiple operations without tangling them up?
To test that, they used a 3x3 motif grid experiment. They taught the model isolated operations, relocation, rotation, reflection, and color swapping, then asked it to combine them, like rotating a shape and relocating it in the same step.
And the results are really revealing about how vector spaces represent distinct concepts.
Yeah, relocation and rotation work perfectly in isolation. And composed together, flawless, every single time.
Oh, wow.
Reflection works perfectly alone too, and composed with relocation, it still succeeds the majority of the time.
But then we get to the color swap.
Yeah, color swapping is highly brittle here. It learns it on a fixed color layout, but if you ask it to compose a color swap with a spatial relocation, it fails completely. 0 successes.
It's like trying to rub your stomach and pat your head while riding a unicycle.
Basically, yeah.
In the latent space, the mathematical idea of a pixel's color is deeply tangled with its spatial location. So shifting the coordinates accidentally scrambles the math, holding the color info.
It just can't decouple them. And this is the absolute frontier of latent reasoning, figuring out how to keep orthogonal concepts orthogonal in a continuous vector space so they don't overwrite each other.
Right. Now, setting the color tangling aside, I want to highlight something that will make deployment engineers very happy. You can actually turn a dial on the model's thinking effort at inference time.
Yeah, this is such a cool feature.
Because reasoning is just iterative forward passes, you can literally tell the API to run more or fewer iterations depending on your latency budget.
They empirically tested this with 3 effort levels, basically controlling the latent iterations or H sub R steps. At the LW setting, it scored 21% pass at 2, but gave a 22% reduction in compute cost.
Nice.
Medium scored 27% with an 11% cost reduction. And high GH effort hit that headline 29.5% score.
This is massive for production. It proves that scaling pure latent compute directly scales performance. You aren't paying for arbitrary text tokens you don't need, just raw mathematical transformations.
Exactly.
If a task is easy, turn the dial down, run fewer iterations, save money. Complex logic puzzle. Crank it up, and the model thinks harder without uttering a word or blowing up your KV cache.
It's a completely different lever for test time compute. With autoregressive models, you have to parse a verbal rationale and you're bound by token speeds. Here, you just allocate raw floating point operations. Clean, predictable, scalable.
Let's bring all this together. BDH-CQ proves continuous latent thoughts work exceptionally well for complex visual and logical reasoning.
Yeah.
By separating recurrent memory from a latent reasoning workspace, we get fast, in-context learning without the latency, memory footprint, or financial cost of decoding intermediate thoughts to text.
And what's truly exciting is where this goes next. Early scaling experiments in the paper show this architecture obeys transformer-like scaling laws all the way up to 600 billion parameters.
Wow, so the math holds up at frontier scale.
It really does.
Which leaves you with a final thought to mull over. If a tiny 150 million parameter model can carve out a brand new state-of-the-art efficiency frontier using pure latent reasoning, what happens when they scale this to a trillion parameters?
Yeah, just imagine that.
Imagine a massive multimodal model that can seamlessly switch between silent, lightning-fast, latent computation for complex logic and verbalized chain of thought only when it specifically needs to call an API or verify a fact.
Right.
The era of models blindly talking to themselves for every single step might be coming to an end. The future of inference might just be silent. We'll see you next time on AI Paper Slop.